Howdy, stranger. Welcome to part 2 of this series. In part 1, we managed to get the game compiling, running, and eventually rendering the main menu graphics. To draw the 3D models in the main menu, we used the same method used by the original game, where each primitive is sent through the render pipeline one at a time. This works fine for scenarios where we have a really small amount of triangles to draw in each frame, but is not really how modern GPUs are designed to work, as each triangle requires one draw call, and each draw call incurs some overhead. As we move on to the in-game graphics, we will change how we do things, namely that we start uploading each object into the GPU as a collection of triangles, thereby only requiring one draw call per object instead of per triangle. Without further ado, let's get to it. Picking up where we left off in the first part, let's take another look at main.cpp and see where we end up when we try to start a race. We last looked inside this function called menu control, so let's put a breakpoint immediately after it and take a look at what happens next. We have a beautifully named variable here called andybodge in an if statement, which is checking if its value is 2. The word bodge shows up a lot in this code base, and even though it's probably an accurate description, it doesn't help to understand the logic a whole lot. In case you didn't know, to bodge something is to do it in a suboptimal manner. Well, in this case it seems andybodge was not set to 2, so we skipped the whole if statement and called setDrawDistance instead with a value of 65,535, which is the maximum value of a 16-bit integer. The value, as well as half of it, is cached in libgte.cpp, referring to the PlayStation's geometry transform engine, so it's likely irrelevant to us as we won't stick to the rather low draw distance of the original game anyway. Next up, we set a path to load a texture for the current racetrack. My guess is that this is probably a loading screen. We then have a call to clear the ordering table, which we can comment out, and then we load the texture using JJS load 16-bit texture. That function's already familiar to us as we previously used it to load images such as the title screen and main menu background. Following that, the code would copy a palette called shield palette presumably into some memory to be used by the old direct draw renderer, followed by a couple more calls to clear the ordering table and swap the screen. I'm not sure why they wanted the game to wait a couple of frames here without drawing anything. Maybe this was a workaround for some kind of bug, if I had to guess, but we'll comment this stuff out as it does nothing except waste time and we want everything to load as quickly as possible. Now we set up another path to load another texture, which leads us into SJR load texture BMP. We previously changed SJR load texture BMP menu to work with our OpenGL renderer, but beyond commenting out some code, we have yet to touch this one. It looks like it does the same bit shifting as our other texture loading functions, so I guess we pretty much just need to add the same stuff we had for the menu here. There seems to be a call to a function called chopup for textures with an ID below 320, so we'll leave that in for now. After the textures are loaded, we go into a function called race, which lives in ayrace.cpp. This function has some initial setup of parameters for the race, and eventually calls race control, so let's take a look in there. As the ASCII art implies, this is the overarching game state logic for one tick of the game itself. We have all sorts of checks for button presses, as well as calls to update various subsystems in here, like weapons and camera. Comments are always helpful, especially such as these at the end of a scope to tell us that this bracket is the end of a switch statement, and the one below is the end if load a bollocks. Very nice. Note these 3 commented out lines to adjust engine sound, adjust crowd sound, and adjust remote engine sound. As I recall, there were really no engine or crowd sounds in the game, but once we're done with rendering and move over to audio, we will revisit these functions and see if we can and should reinstate them. Another fantastic comment here for the following section stating, draw, mesh, auto mesh, reject, don't reject, nurse, bend over, abuse and call a naughty boy track code. Good to know, I'll make sure to keep that in mind. A commented out printf statement with the message "am retiring," which I guess from looking at the code was used to test the code which runs when a player exits the race and not a career decision from the developer. A few more commented out lines towards the end of the function with comments saying they were some sort of bodge. They really like that word. Alright, back to the race function. For some reason this race control function gets called 3 times before we move into the actual in-game loop, which will run until the race ends. The loop itself, of course, calls race control internally once per frame. Let's add a call to set render begin at the top of the loop to clear the frame buffer and get us ready for drawing a new frame. The rest of this code seems fairly self-explanatory, except for this call to move donkey, which apparently only happens on tracks number 8 and 11. There's also a commented out call to Aurora Borealis on track number 13. That sounds pretty, so we might take a look at that function, if it even exists, later as well. Finally, we find some code to draw in-game things. We have draw weapons, draw target icon, draw effects, draw landscape, draw shadow, draw ships, draw all track, draw new track, and a draw object fixed ASM for the sky. The rest seems to be UI and HUD related, so we'll ignore those for now. Let's try to tackle draw landscape first. Okay, so it appears the track is split into sections, with each section containing a list of objects it contains. The section we use is whatever one the camera contains, presumably that means the part of the track where the camera currently is, and we just iterate over every object and draw it. We'll comment this out and start re-implementing it in our own way. Instead of just the objects in the current section, we will iterate over all the sections of the track and get all the objects. Let's add some constants to help us out here. I figured out the numbers in these constants by simply loading all the tracks individually and counting how many things there were in a loop. Some of the track objects contain sprites, so we'll add a struct to hold the data we need to draw those. As stated in the intro, we will not draw the in-game graphics with one draw call per triangle. Instead, the track objects are going to be uploaded to the GPU as vertex buffer objects, or VBOs for short. For each VBO, we also need to store a size parameter which holds the number of vertices contained in the VBO. We will need that when we want to draw the VBO to make sure we draw all of the uploaded triangles along with the texture, which corresponds to this 3D mesh. The objects can also contain untextured colored triangles, so we will have one VBO and size parameter for those. Finally, we also store an array of sprites for each object. To recap, each landscape object is made up of multiple separate groups of textured triangles which we upload into VBOs, along with some untextured triangles as well as some sprites. Now the landscape drawing function can simply iterate over all the track sections, iterating over every object in each section, checking if the object is valid, and in case it is, we will issue a draw call to the corresponding VBOs. We will first grab the matrices for the object's transform as well as the camera and pass those to our renderer. We will also enable depth buffer writes and reads here as that's required for all the 3D stuff, and we will enable blending just in case we have some transparent shapes, and we will disable vertex culling for now as we're not sure about the vertex winding order. Finally, we can iterate over each object's VBO and draw them along with any sprites the object might contain. Before we can finish this part, we need to add some code to our renderer to draw our VBOs. Let's add two methods, one of which will draw textured and the other untextured VBOs. Again, the code for this is pretty much boilerplate OpenGL stuff. We bind a vertex array, which we already set up before, bind the VBO, bind the shader program, and call GLDrawArrays. For the textured version, we of course also need to bind the texture, and we will pass the shader a parameter to ignore all black pixels. Now we can go back to the landscape drawing function and add the calls to our new rendering functions. In order to draw the sprites correctly, we actually need to add a little bit more code. The sprites in the game will be for things like the trees on the side of the road, and they need to always face the camera, a technique commonly known as billboard sprites. To help do this, we will add a function to our renderer which extracts a normalized vector for the camera's right axis. We only need this vector to calculate the vertices for the sprite, as we only want it to rotate horizontally but not vertically, so the up axis is always a constant. With the vertex positions calculated, we pass the sprite over to the renderer, and that should do it for the landscape drawing. At the end of the loop, we need to switch over to the next track section. Luckily for us, the sections contain a pointer for the next section in a linked list, so we can simply use that. Testing our code so far shows nothing, which is to be expected as we haven't actually filled our VBOs with any data yet. Let's do that next. The idea is to preload all the track landscape object data at the beginning of each race, so we'll jump into the race_init function and add our code there after the track data has been loaded by the game. We will add two methods to do this, one called landscape_gl_preload, which will iterate over all the track sections and create the required data to draw them, along with a helper function called createGLObjectBuffer, which takes the ID for one landscape object and actually creates the VBOs and sprite data. We'll set up the helper function first. It will clear any previous values stored in our cache, and then, if the current object is valid, it will set up the required vertex data. Let's define some structs to hold our vertex data, as it will make our life slightly easier than just using untyped arrays of floating point values. The code to create the vertex data is very similar to what we already used in the main menu to draw the rotating ships. At this point, we need one more helper function to find a texture slot. This is just a small optimization so we can group all vertices using the same texture together, as that will lead to fewer VBOs being required as well as less performance overhead by reducing the number of total draw calls required for each landscape object. We'll call this function findSlot, and it will iterate over the list of used textures to see if we already have the current texture in our list. If it finds one, it will return the index for the slot containing the previously added vertex data, and if not, it will create a new buffer to hold vertex data. Once again, I will skip over the conversion code for all the different primitive types into vertex data our renderer can use. Suffice to say, it's pretty much the same stuff as used by the main menu code, except it stores the converted vertex data to our landscape object cache. Now we need a few more functions in our renderer. We need to be able to create our VBOs as well as upload vertex data to them. Finally, we can add calls to these new functions in our landscape object loading function. We check if a VBO already exists, and if it does, we just upload the new vertices. If not, we create one. Note that after uploading the vertices to the GPU, we can call free to deallocate the vertex data from RAM, otherwise we're just leaking memory. Now we can fill up our landscape preloading function. We will iterate over all the objects, and if the object doesn't exist, we should remove any previously created VBO. This requires one more function in our renderer, which simply deletes a VBO. We do this in case we had already loaded one track. Once we load a second one, we can reuse the VBOs and just replace their data, but we have to clear up any which are left over. We also clear up the colored vertex and sprite data here. On second glance, we should also delete the colored vertex VBO here, but that will be left as an exercise for the viewer. Last but not least, we can iterate over all the track sections and cache the landscape objects for them. Some objects are repeated twice, probably since the original game only rendered one track section at a time, so we will use an array of booleans to mark whether an object has already been loaded. If it has, we skip loading it again a second time. Alright, let's test this and see what we get. Absolutely nothing. Time to debug our landscape preloading function with a breakpoint. Our array of booleans is not initialized properly, so it contains random data. We need to sort that out first, as having values of true in there will make the code skip loading the objects. Testing again, and the code is crashing upon trying to deallocate the temporary vertex data. Another array was not initialized with correct values. This time the textured vertex counts. Let's set them all to 0 and try again. Well, it's certainly drawing something, but it's not quite what I was expecting to see. Let's take another look at what we just wrote and see if we can spot any mistakes. Well, this is probably not the actual issue, but this loop should also clear the arrays of texture pages as well as the size arrays. This block is also inside the wrong scope. It belongs outside of this loop like this. Here's a mistake which definitely needs fixing. We should be using the O index instead of the number 0 here to get the various object IDs. Let's take another look. Alright, this is now broken because we've started reusing the old vertex array objects with new vertex buffer objects in our renderer, and it looks like the vertex attributes are not correctly set during the draw calls. I'm too lazy to create new VAOs for all the track objects, so instead we have to tell OpenGL about the different vertex attributes after we bind each vertex buffer object. Luckily, we have a function which already does this called initShaderBindings, which in retrospect is probably not the best name for it, but whatever. Adding this to our drawing methods should fix the issue. It does, however now the landscape appears to be upside down and backwards. We can fix this by inverting the second and third columns of our view matrix. Wonderful, the landscape finally appears to be rendered correctly. Now we can move on to a slightly trickier part, which is the track itself. Before we jump into the code, it's worth taking a look at how the track is rendered in the original version of the game. If we load up the PlayStation version into an emulator and add wireframe drawing on top of the image to show the triangles, we can see that the track is rendered in segments with decreasing levels of detail over distance. Closest to the camera, we have the most detail with the highest amount of triangles, then a medium level of detail where the triangles are twice as big. Further away still, we have the lowest detail, with triangles twice as big as the medium detail. It's effectively a really basic version of what we call tessellation in modern rendering terms. This was likely necessary due to the way textures were rendered by the PlayStation, namely something called a fine texture mapping, which caused the textures to warp as the camera moved and is actually a defining part of how OG PlayStation games looked. The smaller the triangles, the less visible warping there was, so close to the camera you want a high level of detail. For performance reasons, they probably couldn't just draw all the visible sections of the track with this many polygons, thus the need for a dynamic level of detail system. We are no longer limited by our hardware in terms of performance, nor due to a fine texture warping, so we will not bother re-implementing this whole thing as it was. In fact, we can push the game to render the entire track instead of just a few visible sections, and we will render all of it at the highest level of detail, just because we can. So it seems we have a branch leading to two separate implementations of the track drawing code here. namely draw all track and draw new track, which take the same parameters. Quick check with a breakpoint shows the draw new track variant is called. Let's take a quick look at it. Okay, so we have 3 loops which draw the sections of the track, each in a different level of detail. Let's take a look at the draw all track function now. It looks pretty similar on the surface. Alright then, we will comment out everything except the call to draw all track, as that name more accurately describes what we're going to do. Let's comment out all the old code in the function, as we'll replace it with a new version soon. Before we can draw the track, we have to preload it, similarly to what we just did for the landscape objects. In this case, we have to do it after this call to ASM generate tiles, as that function is setting up data for the textures used by the track polygons. We'll create a new function called trackDataGL preload, which will load all the track sections into our OpenGL renderer. Since we're going to load and draw the entire track instead of individual sections, we can do a bit of preemptive optimization here by grouping all of the triangles by the texture they use. For this, we need to know the maximum amount of unique textures used by each track so we can create a cache big enough to hold our data. Luckily for you, I've already gone through the effort of figuring out how many textures are used by loading each track and looping through all the sections and counting all the unique textures they used. There are 7 tracks in total, and these are the numbers of used textures by each of them, with 173 being the largest value, so setting this constant to 174 should cover all of them. I also did a similar process to count the number of track sections per track, and the highest number there was 128 unique sections, which is a nice round number we can put into a constant here. Now we will create a few arrays which will cache the OpenGL VBO IDs as well as the number of polygons contained in each VBO. Additionally, we need to store an array which contains the texture pages, or surface IDs as we called them before, that are used by each VBO. Now we can comment out a bunch of this old code and variables which we won't be using anyway. In fact, pretty much everything in this file can be commented out or removed, as there's a lot of code which would draw one triangle at a time in the 3 possible levels of detail. Back to our function to preload the track data. Let's just move it to the bottom of the file so it's easier to jump to instead of having it in the middle of a bunch of commented out code. As a first step, we will iterate over all the track data cache arrays and zero out the values, since these are static arrays which will be reused whenever we load a new track. We'll add a constant for the level of detail called quality and set it to 2, meaning high detail, with 1 meaning medium detail and 0 for low detail. For the preloading, we will also need a few more arrays to count the number of tiles per texture page. To make this process easier, we can pre-calculate the amount of texture pages needed, which we will do in a separate function. We will also need an array to store the indices of the tiles. This will hopefully make sense in a while once we get to the actual track data. For now, let's implement the tile storage pre-calculation function. This function will take a pointer to our num tiles per page array, as well as the intended detail level and a boolean which will allow us to filter out the weapon pads. It will return an integer with the number of pages used. The weapons filtering flag will be used later to update just the weapon pads on the track without having to touch any of the rest of the track data. We'll iterate over every section of the track, and for each section, we will iterate over every face. The track faces have bitwise flags which indicate what kind of face it is, which we can use here to implement our filtering. Each face can also have a flipped texture, so we need to check that flag before we extract the respective surface. Now we need to get the correct texture for the current tile in the surface. For this, we will implement yet another helper function called getTextPageForTile, which basically just returns a texture surface ID as well as some integer offsets. Once again, we need a static array with some constant values, this time to map the track surface textures to our OpenGL textures. These values are a product of lots of trial and error, along with checking the original track rendering code. Once again, the resulting function looks a bit hacky and should probably be rewritten at some point, but it gets the job done. I think the original textures each had a unique ID in the PlayStation version of the game, but were later packed into texture atlases for the ATI 3D Rage version of the game, and this code is basically just implementing the mapping from one to the other. Now we can get back to our pre-calculation function, where we use the texture ID of the current tile, and we increment the counter of tiles per page as well as the total number of used pages whenever we see a new texture ID. For the medium quality, it's basically the same thing, except there are 4 tiles per surface, and for the high quality, there are 16 tiles per surface. Alright, now back to the track preloading, where we will use the newly created pre-calculation function. Now we need an array to store the number of vertices for each texture, another array of pointers to the actual vertex data, as well as the current texture slot. We'll then iterate over each texture page, skip it if the pre-calculation found no tiles for that page, and store the page as well as the number of tiles multiplied by 6, 2 triangles with 3 vertices each, for a tile, and allocate enough memory for the vertex data. These are all stored using the current slot as an index. Looks like the compiler doesn't know what malloc is, so we'll quickly add an include for the standard library header. Next, we will store the current slot value into our tile storage index array and increment current slot. Let's also add a check to make sure we haven't overflowed the slot data for some reason, although this should never be called. Now we can iterate over all the track sections and preload them, which we will once more write a separate function for, and we'll call it preload section. This function will look a lot like the pre-calculation one, except it will actually extract the vertices and not just count the texture pages used. Once we actually create the vertices, we need a new helper macro to convert the vertex color data. We'll call it toRGB_call2 because I'm not feeling particularly creative, and it's very similar to the first version of this macro, except it casts the color values to unsigned cars instead of GL floats before dividing by 127. The math that tessellates the vertices to higher levels of detail is just copied and pasted from the original code, and then converted to values our renderer can use. On second thought, let's add a second variant of the macro which converts UV coordinates as well. This version is similar to the first one, but divides the values by 31 instead of 255 as the track textures are 32 pixels wide and tall. Okay, by now you get the gist of what this code does. I'll skip to the completed versions of the medium and high quality branches of code as it's quite repetitive. Very quickly, here's what they look like. Finally, we get to the last part of the track preloading function. We'll iterate over each texture slot, and in case our pre-calculation step failed somehow, we will abort. Once again, this check should never fail if our previous code is correct. It's more of a sanity check than anything else. Then we create a vertex buffer object with the vertices we just created and cache that into our track VBOs array. At this point, we don't need the temporary vertices in RAM as we already uploaded them to the GPU and we can deallocate them. That's it for this part. Now we can actually add some code to draw the VBOs. So let's jump back into the draw all track function and start by grabbing the camera matrix. We'll send it over to our renderer, so we have to add an include here, and then we can set up all the rendering parameters. We'll enable writing to our def buffer, and we'll call a new function which we'll name renderGLTrackData. I'll implement this function in the track ASM file as it already contains all the constants and VBO data we need. It's simply going to iterate over all the track data, skipping over the empty ones and drawing the VBOs for the texture pages which actually contain the vertices. To finish up, we'll declare the renderGLTrackData in the track ASM header so it's visible to the outside. Looks like it failed to compile because of all the old track code we commented out. Fine, time to comment out both the declarations of these old functions as well as any calls to them. Alright, now it compiles. Let's take a look. The track is not drawn because we didn't actually add a call to the preloading function. Let's add that call as well as the declaration in the header. Now we finally see the track, but for some reason it's all red. Deja vu to rendering the 3D models in the main menu. Somewhere there's probably some code which is changing the vertex colors using some palette. If we look at where the track data is loaded, there's a function called initFaces, and at the end we have a loop which is indeed changing the colors with the same find nearest color index function. Let's get rid of that so we can see the colors which are actually stored in the track data. Very nice, the track looks correct now, but the speed up pads and the weapon pads look incorrect. The speed up pads are supposed to be blue, and the weapon pads glow in different colors and turn grey when a ship flies over them and a weapon is picked up. We can now fix that by updating just the track vertices containing those every frame. We'll add a new function for that, which looks a lot like our track preloading function, except this time we will filter the weapons in the tile storage precalculation and section preloading functions. In this case, we also need to figure out what VBO index these weapon and speed up pads were in, so we'll get that by iterating over the track texture pages array. At the end, we will update the previous VBO with the new vertex data, unless for some reason it doesn't exist, in which case we create it. Let's see if this makes the pads update. Nope, they're still the wrong color and static, so let's try to fix that real quick. We have this function here called setTrackAttributes in dynam.cpp, which is setting the values of the weapon pads faces. We'll swap out this code with some code which was used in the direct 3D drawing code. This now makes the speed up pads look correct, but the weapon pads still need a bit more work. In weapon.cpp, we also have this function called cycleWeaponGrids, where once again the weapon pad colors are changed to red. This function has the logic for the actual cycling of different colors and setting them to white whenever a weapon has been picked up and the pad is inactive. We'll replace these constants, which apparently were changed for the PC version of the game, with the color values calculated with some sine curves just above here, and that should do it. Now the track looks as expected, but as you've probably noticed, the frame rate is pretty abysmal. We'll fix that in a bit, but first let's add the ships. Looking at the function draw ships, we find that it iterates over all the ships and first performs some kind of distance check between each ship and the camera position to determine if the ships are visible or not. Once again, this was clearly a performance optimization, which we can get rid of, as we'll just draw all of the ships all of the time. After that, depending on the distance, it will pick a different copy of the ship in decreasing levels of detail as the distance increases. We don't care about any of that, as we'll just draw the highest detail ships all the time. Finally, we have some logic to determine if we should skip drawing the player's own ship when using the first-person camera view, and we call drawObjectASM to actually draw the ship. Taking a look inside reveals yet another fairly large function which draws an object one primitive at a time. We could of course preload the ships into VBOs as we did with the track and landscape, but since we already wrote this kind of code for the main menu, we'll just be lazy and do the same here. We'll comment out all the old drawing code, set up our own camera and object matrices, and finally add a function to draw the primitives. We could have reused the same code from the main menu, and this would be a perfect place to do some refactoring later, but that's left as an exercise for the viewer. Now we'll just do basically the exact same thing as in the main menu object drawing code, except we also allow for transparent vertices. As far as I know, the only transparent vertices in the ships are the flames coming out of the jets in the back of the ships. I'll show the first primitive type and skip the rest, as you can just refer to the main menu drawing code when in doubt about the other primitives. It fails to compile because we didn't add a forward declaration to this new drawing function. Interestingly, this ndscn.cpp file doesn't even include its own header, so we'll just move the forward declaration to the top of the CPP file. Quick and dirty, but it works. The game compiles and it renders the ships as intended. The black background is not particularly pleasing aesthetically, so let's take a look at how the sky is drawn next. Apparently the sky is just drawn with a call to draw object fixed ASM, and it's actually the only thing using that function. Looking inside, there are no surprises. It's once again drawing primitives one at a time, but this time with a fixed depth value and rotated based on the camera rotation. Makes sense, but we can simplify this a whole lot. Let's comment out the whole thing and copy over the code from drawObjectASM. Then we can just change the model matrix to the identity one, as the intended effect is that the sky moves with the camera. We'll set the view matrix position to 0 as well as the camera position, as we only care about the camera rotation. Next we disable depth right and read, as literally everything should be drawn on top of the sky. Blending is also not needed here, as there's nothing behind the sky. That should do it for the drawing code. Let's see what this does. Okay, cool. It does draw the sky as intended. You can even see from the shape that they use the dome shape for it instead of the traditional skybox, which would become popular a few years later. Unfortunately, the sky is now drawn on top of all the other 3D stuff, so let's fix that real quick. Simply moving the call to draw the sky to before any other 3D stuff is drawn should do it, and it does. The game is starting to look pretty decent now. There was a commented out call to a function called Aurora Borealis, which is slightly misspelled, but in case you don't know, it refers to a psychedelic looking atmospheric effect, which occasionally happens in particularly cold countries, usually in places like the Nordic European countries and Alaska. I'm not sure why it was commented out here, but I imagine the conversation at the time went something like this.
Good Lord, what is happening in there?
Aurora Borealis?
Aurora Borealis. At this time of year, at this time of day, in this part of the country, localized entirely within your kitchen.
Yes.
May I see it?
No.
Even though it's only implemented for track number 13, let's see if we can get this to work. The thing is, the game only has 7 tracks, so the numbers above 7 probably refer to the higher difficulty versions, known in the game as Rapier class, which are unlocked after winning the championship in easy mode, referred to in the game as Venom class. We are not going to play through the entire game though, as we have the source, so we can just cheat. A quick search for the word cheat shows us this comment in main.cpp which says you can enable a cheat permanently by setting a few values. Let's uncomment the cheat and try again. Nice. The Firestar track is now also shown in the track selection menu, and we can also play in Rapier class now. Our breakpoint confirms that track number 13 is Silverstream in Rapier class, and taking a look inside the Aurora Borealis function, we see that it's doing some math to change the vertex colors of the sky object using some sine waves. In-game, we can kind of tell that that's happening, but the frame rate is so bad that it hurts the eyes. Let's see if we can improve that. At the end of the game loop, we have some math to calculate the frame rate. It looks like it's updating the value every 5 frames, which is fine. There's even some code to show the frame rate value on the screen, toggled by a variable called FrameState. It looks like it should be toggled by pressing Ctrl-Shift-F11, but a quick test proves that it's not working. That's not unexpected, as we wrote our own input handling, so this code is probably not even getting called. Fine, let's just make it so that the counter is always shown for now. Wow. According to the game, we're getting a smooth 10 FPS currently, and that sounds about right based on how it looks right now. I first tried out just commenting out stuff from the main game loop to try to see what was eating up all of our performance, and then it occurred to me that the culprit might actually be the landscape drawing code. The thing is that the way the game originally drew only a few sections of track at a time meant that the landscape data had to be set up in such a way that each track section contained all of the surrounding landscape objects. In other words, a lot of the landscape objects are repeated in multiple sections of the track, and since we're drawing all the track sections now, we're also probably drawing every landscape object multiple times for no reason. Luckily, we can easily fix this by adding an array of booleans where we mark each object ID as rendered the first time we draw it, and skip any subsequent calls to draw it. Lo and behold, the frame rate is now somewhere between 142 and 166, which is limited by my current display refresh rate, which if I recall correctly is set to 155 Hz. Of course, the game logic only updates at 30 frames per second due to the way it's coded, but changing that is a task for another day. The Aurora Borealis effect also looks a lot cooler now, although it's running a bit too fast as it's tied to the frame rate, but we'll leave it as it is for now. The only thing missing now at a quick glance is the shadows for the ships, so let's tackle that. Right, so looking at the draw shadow function, we have a loop which iterates over all the ships, checks if they're visible, then calculates 3 position vectors corresponding to the ship's nose and wings, takes a point on the face of the track section under the ship, and performs a collision check under a function called plane line collision between the 3 ship positions and the track, using the normal of the track face to define a plane. The rest of the function figures out where to put polygons for the shadow, so they're on top of the track but under the ship, and draws the resulting shadow polygons. We'll keep the first part but discard the rest, as the original shadow implementation didn't look great. As the comment says, their method is fast but results in inaccurate sorting, so we'll try to improve upon it a little bit. You can actually see how the original implementation fails in some scenarios here. As the ship crashes and bounces up and down, the shadow will clip through the ship, occasionally ending up drawn on top of it. We'll keep the plane line collision call, as it's probably about as accurate as we need it, but we'll change up the calculations after it. Instead of just doing a bit shift to the right by 12 bits, we'll do the same thing by converting the value to a float and dividing by 4096 in an attempt to get a bit more precision out of this. I'm not sure if this actually helps, as looking at the plane line collision, it's also only using fixed point integer math, but it seemed like a good idea. Now we can create the vertices, but instead of the 3 original vertices, we will create 6, where the last 3 are the midpoints between the first 3. I did this because the original game rendered the shadow as 4 triangles, which can be seen here. We probably could have gotten away with just 1 triangle, but this way we can warp the shadow to sort of wrap onto the slopes of the track a little bit, as that's why this method calculates 3 different line-to-plane collisions in the first place instead of just checking for 1 point directly below the ship. Now we can add code to create our vertices and draw the 4 triangles. Testing it shows there's no visible shadow though, so let's take another look at the code. There's a chance that our shadow vertices are a bit too close to the track vertices, so we can introduce a variable to control the distance to the ground. Let's call it closeness and set it to 0.9 to try to multiply the amount by which we move the shadow points downward from the ship. The shadows are still not visible, so let's try something else. Let's comment out the rendering of the track and landscape objects and see if there's any shadow under the ship. We'll also disable blending, the discarding of black pixels, and we'll set the alpha value of the triangles to fully opaque just to be sure none of those things is the cause. Alright, now we can see the shadow, so at least we know that the shadow drawing code works. We can bring back the black pixel discarding and test so we can rule that out as the issue. Alright, so if none of those things are the problem, let's do something different and add a new blending mode just for the shadows. So far we only had blending disabled or enabled with the standard source alpha, 1 - source alpha function, but the shadows are going to look best with a multiply blend, and later on, for the weapon effects, we will use an additive blend. Now that the function signature has changed, we have to quickly update all the places where it's called, and then we can try it out on the shadow rendering. Okay, that looks pretty good. Let's bring back the track and landscape rendering now and test again. Well, the shadow looks good, but the track is semi-transparent. Looks like I accidentally enabled blending when drawing the track. And the shadow disappeared again. What is going on here? Okay, I finally figured it out. When we draw the shadow, we disable the depth rights. After that, we draw the track, which gets drawn on top of the shadow. If we just draw the track before we draw the shadow, it should finally work. There it is. Now we can set the alpha to 0.5 and call it done. Looks good to me. Let's move on. Back in the game loop, we can bring back this rescue droid code I commented out earlier. It seems to be just updating the skeleton with the position and rotation, and then calling transform static object to draw it. Luckily, we've already implemented that, so there's nothing else we need to do here. We already know this works because we could see the rescue droid moving at the start of the race. Now we can take a look at the draw weapons function to see what needs to be updated to make it work. Okay, so first of all we have this call to draw internal shield, which just makes the whole screen slightly blue. It sets up a polygon of type F4, which is an untextured flat shaded quad, and as the comment says, the HUD should not be affected. So let's comment this old code out and write our own. The original code shows the color is set to a constant white 2 translucent, which we can find in the code as converting to RGB values of 100, 100, 100. We're just going to draw a full screen colored quad, but we'll change the color to be blue instead of white, as that's how it looked in the original PlayStation version of the game. We'll ignore depth buffer reads and writes, enable blend, and draw the quad. That's that. Next up we have two calls to transform static object bodge and transform static object, where the bodge version is only used to draw the shield when the camera is outside of the ship. Once again, it's a whole lot of code to draw primitives, likely just copied and pasted from somewhere else in the code. Let's comment out the whole function and write our own version as usual. Since this is only used for the shield, there are only two types of primitives used, G3 and G4, which are go-route shaded triangles and quads, so we only have to implement those. For the other weapons, the code calls transform static object, which is already implemented, so we don't need to do anything else there. Next up we have a call to draw target icon, which will draw a diamond shape around a ship in front of you when you have a homing weapon to show where it will hit. This one will require a helper method, which we'll add to our GL renderer, which will transform a point in 3D space to screen space. This will let us draw the square texture such that it always faces the camera but tracks the ship in 3 dimensions. We'll set the alpha channel to a slightly transparent 0.75, and then we can wrap this up by drawing the textured quad. Let's run the game and try to pick up some weapons to see if our code is working. Immediately we pick up a shield and realize the outside ship view does not look right, the inside shield view doesn't draw at all, but at least the mines look alright. Let's take a look at that shield drawing code again. We forgot to add a line to set the camera position for our renderer, but that's not really being used yet, so that shouldn't be the issue. The rest of the code looks alright, so the issue is probably related to the order of the draw calls again. Let's move the weapon drawing calls down a bit so they happen after the other 3D stuff is drawn. The targeting indicator seems to be working alright, and the outside shield looks better, but the inside view is broken. Also, the game is crashing after a while because of an uninitialized variable. This is happening inside the AI ship update code, which means it will probably happen a lot, so let's fix that before we move on. The variable in question is a pointer to a face from the track. It's declared at the top of the update remote chip function, then it's set to some value in the first branch of code, but indeed it is not initialized in this branch. Let's see what's going on here. So the update control function pointer for the ship is set to this hold center function, which is called with the face pointer variable. The hold center function doesn't even use the face pointer parameter, so it doesn't even matter that it's not initialized, it's just the compiler being overtly cautious. Let's just set it to null when it's declared and move on. The proper fix, of course, would be to fix the hold center function to not even take any parameters apart from the result vector, which it's zeroing out. Okay, now to check what's wrong with the internal shield view code. Whoops, it's calling code to render a 3D colored quad when it should be a 2D one. The thing is, we don't have a function to draw 2D colored quads, so we'll have to add it. That will also require a new shader binding, and since the shader code is exactly the same as the 3D version, we can just remove the 3D part from its name. The function, of course, only takes a bunch of vertices as input since no texture is used. Alright, now back to the outside view of the shield. It almost looks good, but the colors are a bit off, so let's try to find where they're set. We have a function to initialize the shield and another to update it. Init shield doesn't touch the color data, but update shield does, and as usual it's being set to some fairly weird values, presumably for the PC version of the game back when it didn't support all the colors that the PlayStation did. Since I don't know what the values were for the PlayStation version, I can only take a best guess here, which is that the values which are calculated with the sine curve go into the red and green channels, whilst the blue channel is a constant fully blue. That way it should give us colors which shift between blue and white. It's annoying to play the game and not know which weapon we currently have equipped, so let's quickly implement the draw weapon sprite icons function to get that working. As always, we'll comment out the original drawing code and write our own using the original values as a reference and also using the screen ratio values from our STL window. This is just standard code to draw a 2D sprite similar to our UI stuff from the main menu, so I won't spend any more time explaining it. A quick test shows the weapon icon is too high up, as its top half is outside the screen. Once we fix the Y coordinate in the code, it should be drawn in the correct place. That all looks pretty good, but the inside view of the shield is still not working. That makes sense, as we never passed the projection matrix into the new 2D colored triangle shader, and once we add that, it should finally work. It does. Very nice. Now the only major thing missing from the in-game graphics is code to draw the particles, or effects as they're called in the game code. The add effects function looks fine as it is, but draw effects will need some updating. We'll comment out the old code and set up the usual parameters for our renderer, then iterate over the effects, and as we want these to be drawn as billboard sprites, meaning they're in the 3D scene but always face the camera, we will need the vectors for up and right from the camera's perspective. We already have a helper in our renderer to give us the right camera vector, so we just have to implement a helper to give us the up vector. It's pretty straightforward. Again, we just grab the values from the view matrix and put them in a vector which we normalize, and that's basically it. With these vectors we can now calculate the sprite's up and right corner positions, and with those we can create the corner vertices. From those we can then create the actual vertex data we need to draw, but we will also need one more macro to convert color values for us, as they're stored in R0, G0 and B0 variables this time. That gives us everything we need to draw the sprites, but before we try it out, let's quickly skim through the rest of the effects CPP file to see if we also need to fix any color values. Yep, it certainly looks like these values are not going to look very good, so they need to be replaced. We'll set up our own color values array here and try to see what colors these originally mapped out to. The current version of the code looks like it's using the green channel value to set the color, and as far as I can tell, they will all map out to 100, 100, 100 for red, green and blue respectively. I'm pretty sure the original game had different colors for the various effects, but maybe the textures already have a color, so the vertex colors aren't necessary. We'll set all of these to 50 as our macro is dividing by 127 instead of 255. Further down we have the update function, which also sets up the blue color channel to the constants in the table above, so we'll replace this with our colors as well. We have multiple places here which do the same thing, so let's quickly replace them all and test them out. The missiles have a trail of white smoke, and the electric bolt has the same but in green. At some point it looks like the game stopped emitting new particles, so there's still some work to be done, but at this stage the game is already quite playable. We'll call it a day here and continue in the next episode, where we'll finish up any remaining graphics which are missing, like the win and lose screens, and maybe do some other small tweaks to make the game look a bit better overall. We'll also tackle audio, which we haven't looked into at all yet, so stay tuned for that. If you liked the video, feel free to hit like on the video, but if you don't, then that's also fine. Also, consider subscribing for more content like this, as I'm planning on doing this sort of thing with more games in the future. With that, I say thank you for watching, and I hope to see you on the next one. Later!